Hi everyone, so this is going to be a very short video to compensate for the incredibly long one that I just made you watch. So sorry about that, but it had to be done. Anyway, so until now we've only seen things that are in equilibrium. And remember that equilibrium doesn't mean that things are still, it just means that things are moving at a constant speed. So something that's moving like this is in equilibrium because it's not accelerating. However, in real life, actually, things move and accelerate. And we need to know what happens to things that are accelerating. And that's what Newton's second law tells us. Again, it really helps to imagine things in space, because if you imagine things on Earth, then there's friction and all kinds of stuff, and that makes people confused. So we will imagine that we are in space, and there's a ball. And this ball is just moving like this at a constant speed. That's because that's what balls do in space. They just move at a constant speed. And what we want to do is we want to stop it. Now, if we want to stop it, everybody knows that what you need to do is place yourself in front of the ball and push it backwards. And remember that we will picture the forces acting on the object that they're applied to. So even though this guy is doing the force, it's really acting on the ball. And so then we push it backwards, and then we slow it down until it stops. And then once it's stopped, we can stop pushing, right? And this guy will remain still, because we need a force to accelerate things, and if we don't do any force, then things keep their movement. So this deceleration, this what we're doing is really accelerating the body, in the sense that we are changing its speed. And remember that acceleration is nothing but the change in the speed of something. So somehow the force that we're doing has to be related to the acceleration of this body. The same thing happens if we have another ball and we want it to go faster, right? So if this ball is still and we want it to accelerate, well, everybody knows that we need to push it. So here's my guy, and pushes the ball, and then the ball accelerates. So therefore, we have this idea that when there's a force, there's an acceleration. When there's no force, there's no acceleration. And the more force, of course, more acceleration. So, of course, we can put this in an equation. And we can say, well, okay, so when I do a force on a body, this will create an acceleration, and the acceleration is proportional to the force. Now, both the force and the acceleration are vectors, so I'm going to write a little arrow here to signal this. Because remember, when we do problems now, we need to consider two dimensions, not just one. And that's a little tricky. And between these two quantities, there's a constant of proportionality. And today we know, of course, that this is the mass. And the brilliance of this equation is that it's not just like, oh, look, the more you push, the more something accelerates. This equation actually defines the mass. What is a mass? Well, a mass is something that opposes movement. The more mass, the more I oppose this movement. That's what this constant of proportionality does here. And this is something that we call the inertial mass. And by this we mean that this is a mass that opposes movement, but this says nothing about gravitation, does it? I mean, we could live in a vacuum full of balls like this, and these balls have a mass, and let's say that they don't attract each other because they don't have enough mass, and this mass would still tell us how hard these masses are to accelerate. So how hard it is to change their motion. And the fact that this mass is the same that causes gravity is not obvious at all. And that's why normally we call this mass the inertial mass, to distinguish it from the gravitational mass, which is the source of gravity. And the gravitational mass, of course, now we know that it's exactly the same, but it doesn't have to be. And this is something very subtle that you probably don't understand right now, and you're thinking that I'm, nuts. But hopefully you will understand this subtlety later on in the course. So anyway, this mass that we're considering here is the inertial mass. Okay, and now I'm just going to give you another little example of how we can apply this thing. Here I have the typical pulley that has a little mass and a big mass. I'm going to assume that this mass is bigger than this one. And the floor is somewhere here. So I know that this thing is going to accelerate this way, I just don't know how fast. These two things, of course, are tied by a string that we have over here. Now, naively, you may think, well, acceleration of gravity is g, so the acceleration should be just g. These two things go down with an acceleration g. That's what you would think, and you would be wrong. So let's take a look at what's happening here. In order to do this, we need to be very, very careful, because here we have two different bodies, and we can't just look at the forces on both at the same time. This body has a set of forces acting on it. This body has a set of forces acting on it. The acceleration of this body will be determined by the forces that are acting on it, and the acceleration of this body will be determined by the other forces that are acting on it. These are different bodies, we can't combine them. So every time that we try to solve a problem with forces, we need to consider each body separately. How do they connect? Well, they connect because some of the forces acting on this body will be the same as the forces acting on this body, and therefore we will see that the acceleration of these two bodies is related. But, again, you can't consider the system as a whole, you need to consider the parts. Let's see what I mean. So first thing, I'm going to look at this body here and find which forces are acting on it. I recommend that you stop this video right now and try to say out loud which forces you think there are in it. Or even better, sketch this thing and draw them. Okay, so on this guy, I can identify two forces. The first one is, of course, the weight. Remember, that's the weight, and the value is mg. But we call it the weight, not gravity. There's another force, though. What is the only other object that's actually pushing this thing? Well, it has to be the string, right? This thing wants to go down, but the string is pulling it up. So basically, there's two forces acting on this thing. One pushes down, one pushes up. And the force of the string, we call it the tension. So here's my tension that's pushing this guy up. Now, I want to know the acceleration of this guy. And remember that it's the net force of a body that's equal to the mass times the acceleration. So it's not the weight or the tension that's equal to mass times acceleration. I take all the forces acting on this guy, I add them all up, and that's equal to the mass times the acceleration. Why? Well, because if these two guys were equal, then this would be 0, and there would be no acceleration. So the acceleration can only depend on the total force and the net force. Okay. Now the next thing that I need to do is to choose a sign convention, which is, well, I could say that this points down, so this will be minus, and this points up, so this will be plus, or the other way around. And it doesn't matter. There is no right way to do this. I am going to choose down to be plus and up to be minus, because I know that this thing is going to go down, so this way I will get a positive result. But if you do it the other way around and keep being consistent, you'll have no problem at all. So I'm going to call this plus and this minus. Good. So now let's write Newton's second law. Well, first thing, we need all the forces. We have two forces. W is plus because it points in the plus direction, and T is minus because it points in the negative direction. So I have weight minus tension, that's the total force, that's the net force, and this has to be equal to the mass, which is big M, times the acceleration, and I do not know the acceleration. Now with this, I can't solve anything. And I can't because I don't know the tension. So I need more information. Where can I get more information? Well, obviously not here, it has to be in the other body. So I need to do exactly the same thing for the other body. So in the other body, there will be also two forces. Force number 1 points down, that's the weight, equals mg. And force number 2 will be, again, the tension. And the beauty of this is, remember that in a string, this tension has to be equal to this tension, because the string is not breaking. So here we have that this has to be the tension of the string. Now one more thing about the sign convention. Here I chose this to be plus, this to be minus. So this tension, do you think is going to be plus or minus? Pause the video and tell me. Well, you might have thought that it's plus because it goes up, but actually I could just take this pulley and draw it like this, right? Here's my pulley, here's my string, here's my mass number 1, here's my mass number 2. And you will quickly see that whatever points this way should be plus, whatever points this way should be minus. Because the tension is going this way, then it's going this way, same as the weight, so it should be plus. So this is plus, and then the weight is minus, which makes sense because this tension actually is pulling this up, and is actually going in the same direction as the weight that's pulling this down. So this way we can keep the signs consistent. Okay, so now let's do the same thing. Let's write Newton's second law for this guy, and we will have the weights for the small mass. Let's just write mg, because that's faster. mg, but mg again is negative, so minus mg plus t equals little m a. And here instead of the weight, I'm going to write big M G, because that's what it really is. Okay, and now I have two equations and one unknown. Well, actually two unknowns, also the tension. Now, I can solve this in many ways, but the clever way to do this is just to add up these two equations, because this is positive, this is negative. So if I just add up these two equations, I'm going to get this. So on the right side, so here is MA plus little ma, and doing the associative property, I get m plus m times the acceleration. Now on the left side, I have t, well, minus t plus t, that's just 0. So I can just forget about this. And now I can get mg minus mg. So it's, again, by the associative property, m minus m, g. And now all I need to do, I know this, I know this, I know this, I only don't know this, so I just need to isolate a. So a will be equal to m minus m g divided by m plus m, which is interesting because it's not equal to g. So as you saw, here's the trick. Isolate the bodies, write down all the forces, choose a sign convention, and then write down Newton's second law. Sometimes you have several bodies, write Newton's second law for each body, and then all you need to do is find the unknown that you want to find. That's it. I told you it would be short. So after this, you should be able to draw the forces for each body, choose the sign convention, and apply Newton's second law and solve the equation. That's all there is to it. What's really hard in kinematics is not doing this, is actually identifying what law applies to that situation. And now it's very easy because you always know which law, because that's whatever it is that we're doing right now. In the actual exam, everything will be there at once, and you will have to choose. Is this Newton's second law? Maybe the first law applies, maybe momentum conservation applies. Don't worry about it too much though, because we will also practice choosing the principle in each situation. Anyway, I hope you understood this. If you didn't, of course, you can send me an email or come to see me, and I'll see you in class for practice. See you later.